Hey there, welcome back to Short Takes 331. Today we're going to talk about the exponential form of the Fourier series. So let's jump right in. So recall that the Fourier series for a given function of x takes this form if we want to write this function or consider this function in the interval minus L to L. And so we have an a0 over 2 coefficient and a sum from k equals 1 to infinity of a cosine part and a sine part with corresponding coefficients ak and bk. Now, we also saw in a previous video that we have this Euler's theorem or Euler's identity that tells us that e to the I y for, in fact, any y whatsoever, if it's real or complex, we can write it as cosine y plus I sine y. And if you have a minus sign, then you can consider this to be minus y if you want. E to the minus I y is cosine y minus I sine y. And again, you can think of this as being e to the I minus y. Cosine doesn't care about the minus sign, it's an even function, but the sine is an odd function, so the minus comes right out. And so that's where this minus sign comes from. You can combine these two, add them or subtract them, divide by 2 or by 2i, and you can easily derive these identities. So the cosine of y is e to the I y plus e to the minus I y divided by 2, and the sine of y is e to the I y minus e to the minus I y divided by 2i. So these are classic identities. These are things that if you're interested in a career in physics or astronomy or probably any kind of engineering, you would want to know. You want to know very well, since Fourier series and Fourier transforms play such an important role there. Now, from these identities here, you can imagine inserting these into the cosine and the sine, so each of them in here, and this sort of tells you that there must exist some coefficients ck, which are related by to ak and bk, such that everything can be written in terms of a complex exponential in this way. So in other words, if I put this in here and this in here, then I will get a sum of complex exponentials with positive or negative argument relative to what we see here. So positive k pi x over L or negative k pi x over L. And so everything can be summarized in this form. You can see that those coefficients would have to exist somehow if the AKs and BKs exist. And it's all really just a linear transformation because the relationship between the cosine and the sine and these two complex exponentials is linear. And so the relationship between the AKs and the CKs, or AK, BK, and CKs would have to be linear. So then this is our exponential form of the Fourier series. So f of x is a sum from k equals minus infinity to infinity of ck e to the I k pi x over L. And of course you could consider the minus sign here if you wanted to. It's just as well to define this with a minus sign or not. It amounts to really replacing ck with c of minus k, and you're free to define the Fourier series in this way or with a minus sign. Now, how are these coefficients related? How are the AK, BK, and CK truly related? So to find that out, what we're going to do is we're going to go ahead and take this form and write it out as the sum from minus infinity to infinity. We're going to separate the zero component here, and we're going to separate the positive part from the negative part. And so what I did here is I took from k equals 1 to infinity, and I wrote it as its own thing. And then from k equals minus 1 to minus infinity, I wrote it like this. So I wrote k from 1 to infinity, but c minus k, and then the minus k that goes here, I put the minus sign out here. So that's all I did. And now we can write, we can connect, we can combine these two terms as a single sum from k equals 1 to infinity. And we have ck e to the I k pi x over L, and c minus k e to the minus I k pi x over L. Now that's nice because we can take this exponential and this one, and we can use our Euler identities to write down what they are. And then we can return to cosines and sines. And if you do that, you're going to get a cosine and a sine from this, and a cosine and a minus sign from this. And if you combine those, then you get that the coefficient multiplying the cosine part coming from here and here is just a sum of ck and c minus k. So this is going to be ak. And on the other hand, we have that for the sine, there's going to be a ck and a minus c minus k coming from here. And so, and of course, there's an I in front of the sine in Euler's formula. And so we have I times ck minus c minus k. And this whole thing with the I included is bk. And of course, c0 is a0 over 2. There's nothing interesting there. Now, I've identified these just by looking at our original series. over here, ak, bk. So what plays the role of what? Strictly speaking, if I really want to be careful in how I interpret this as being ak and this as being bk, I would have to invoke the linear independence of these objects, cosine of k pi x over L and sine of k pi x over L. So these are all linearly independent with each other, and also the different cosines with different k's are linearly independent. And so that really is what allows us to say that this coefficient has to be ak, and this whole thing with the I included has to be bk, and of course this guy has to be a0 over 2. Good. By the way, we can then invert that relationship. So this gives us ak and bk in terms of ck, but what about the other way around? Yes, we can do that. You can sum these two. If you multiply bk by minus I to get rid of this I, then you can sum the two, and you can obtain ck, or rather 2ck, so you divide by 2 and you obtain ck, and that's for k greater or equal to 1. You get then that ck is ak minus I bk divided by 2, and for k less than minus 1, less or equal to minus 1, you get ck is ak plus I bk divided by 2. Okay, and that comes simply from the fact that here k is positive, and so if you sum ak plus I, ak minus I bk, then you are left with this ck, and you solve for ck. And if you do the opposite, if you sum ak plus I bk, then you obtain c of minus k, which is the same as saying ck, but for k less or equal to negative 1. In any case, this is the result. So in other words, up here we have the ak's in terms of ck's, and down here we have the ck's in terms of ak, bk. And that's all there is for that part. Now you can tell, and this is interesting, that bk being equal to 0 means that the corresponding ck obeys this, that ck is equal to c of minus k. And this happens, for example, for all k, actually, if your function is even. If your function is even, then the sine part does contribute, all the bk's are 0, and so it means that your ck's have to obey this property, that ck is equal to c of minus k. You can see that here. If this coefficient is bk, which we established, then if all these bk's have to be 0, then ck is equal to c of minus k, and that's again true for even functions. For odd functions, the opposite happens. The bk's survive typically, and the ak's are all 0, which means that ck is equal to minus c of minus k. So that's as far as how the ck's are connected to the ak's, that is to say, how our exponential form of the Fourier series is connected to the conventional form in terms of trigonometric functions. Now, the ck's are actually also defined by an integral, and you can show that by either using these identities, or you can show that in other ways. But it turns out that the ck's are given by this formula, 1 over 2L integral between minus L and L of f of x e to minus I k pi x over L dx. Now remember I said that our Fourier series in exponential form can be defined with a plus sign here, like this, with a plus I k pi x over L, so I didn't write any sign here. But you can also define it with a minus sign, and sometimes it's defined with a minus sign. Well, no matter what you choose here, the opposite sign will appear in this formula. Okay, so if you choose this form with a plus sign, then there has to be a minus sign down here as I wrote. Now we can check for consistency. If we have this formula, is it true that that this formula really returns ck? So what do I mean by that? Is it true that if f of x is written in our exponential Fourier series form, that when I do this integral, I obtain ck? Well, let's try. And for that, I need to change the name of the variable. So you will see why. So let's say q. Let's put a q here, and we'll calculate this, and we ask the question: is that true that doing this calculation we obtain cq? Well, we're going to go ahead and insert for f of x here our Fourier expansion, and so this is why we needed to change the notation to q, because we're going to use k to represent the sum that represents f of x, and so we have the sum of k equals minus infinity to infinity ck, and then we have e to the I pi x over L times k. So this part together ck and the sum are what gives us f of x, and so I inserted then the Fourier series form, the exponential form of the Fourier series for f of x in here, and then I push the integral through the sum, and I'm left with everything that depends on x inside this integral. And it turns out, and I will show you next, that this integral together, the 1 over 2L, is actually delta of kq, so the Kronecker delta of kq. And if you sum over all possible values of k, then that's going to select only the one k that is equal to q, and so that indeed gives us cq. So if we can show then that this integral divided by 2L this whole thing is delta of kq. That is to say that is 1 if k is equal to q and is 0 otherwise, then we're done. Then our job is done because this sum will cover all possible values and we'll select CQ automatically. So let's see. Well, if k is equal to q, then this exponent is 0, then the integrand is 1, and we do the integral between minus L and L, that gives us 2L, divided by 2L is just 1. So that's all there is if k is equal to q, no problem. If k is different from q, is a more general case, then where k and q are arbitrary, but they're different from each other. We're assuming that they're integers, by the way, but they're otherwise arbitrary and different from each other. Then the result of doing this integral is very simple. It's 1 over 2L, that's just along for the ride, L over I pi, and then 1 over k minus q. So we have this prefactor just from doing the integral, and then we have e to the I pi x over L k minus q evaluated at x between L and minus L. So we have to take this function and evaluate it between x equal to L and x equal to minus L. But look what happens in that case. It turns out that if x is equal to L or minus L, we end up with e to the I pi k minus q, or e to the I pi q minus k. Yeah, so x cancels with L if x is equal to L or minus L, and we're left with e to the I pi k minus q, or e to the minus I pi k minus q. In both cases, we end up with something that looks like this: e to the I pi m, or e to the minus I pi m, where m is an integer. Well, it turns out that both give you the same result. So in other words, this function takes on the same values at x equal to L and x equal to minus L. The value happens to be minus 1 to the m, doesn't really matter. What really matters is that these two are identical, and so the two endpoints are identical, which means that our result is 0, which is exactly what we wanted to see. So we wanted to see that this integral gives us delta of kq, the Kronecker delta of kq. So it vanishes if x is different, if k is different from q, and it's equal to 1 if k is equal to q, and so that gives us our final result. And so we confirm then that this formula on the right reproduces indeed ck for our exponential form of the Fourier series. And that is it. That is all I have for you today. I hope you enjoyed this video. I hope you find it useful. If you do, please like and subscribe. And as always, if you're looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you as soon as I can. And I will see you next time.